The average home today costs hundreds of thousands of dollars. For many people, it's the biggest financial commitment of their entire life. And even after buying it, the payments don't stop. Every month there's something else. Heating, cooling, maintenance, repairs, insurance. It's a system that never really ends. Now imagine something very different. A house that costs around $5,000 to build. A house that doesn't rely on constant heating or cooling. A house that, once finished, barely asks anything from you. No large energy bills, no complex systems, no dependence on constant external inputs. And here's the part that doesn't make sense. This kind of house already exists. Not as an experiment, not as a prototype, but as something people have already built and lived in. So the real question isn't whether it works. The real question is, why don't you see it anywhere? Before we go further, if you're the kind of person who likes understanding how things actually work behind the surface, and why some ideas quietly disappear, make sure to subscribe. Because this is just one of many systems that don't fit the world we're used to. Now, let's look at what this house actually is. It's called an Aircrete dome. At first glance, it doesn't even look like a normal house. No sharp corners, no traditional roof, no wooden frame hidden behind drywall, just a curved shell, smooth, continuous, almost like a single piece, and that's exactly what it is. Instead of building walls piece by piece, like stacking wood, insulation, and panels, this structure is created as one unified form. The material itself is surprisingly simple. Aircrete is made from cement, water, and foam. That's it. When mixed together, the foam creates millions of tiny air pockets inside the material. Those pockets do something extremely important. They trap air. And trapped air is one of the best insulators you can have. It's the same principle that keeps a winter jacket warm. The air inside slows down heat movement. But here's where it gets interesting. Unlike insulation inside a wall, this material is the wall. No layers, no gaps, no weak points where heat can escape. Now combine that material with a dome shape. Instead of flat walls and corners, you get a continuous curve. And that changes everything. In a traditional house, heat escapes through joints, where walls meet ceilings, where floors meet foundations. Through studs, gaps, and seams you never even see. But in a dome, those weak points are almost completely gone. The shape itself helps maintain temperature. The material slows down heat transfer. Together, they create something very unusual, a structure that stays stable inside, even when conditions outside change. Hot day? The heat moves slowly through the walls. Cold night? The warmth inside doesn't disappear instantly. It's not about blocking temperature, it's about delaying it. And that delay is what reduces the need for constant heating and cooling. Now think about that for a second. If your house doesn't constantly lose heat, you don't need to constantly replace it. That alone changes the entire equation of how a home operates. And then there's the cost. Because the material is simple, and because the structure doesn't require complex framing, the price can drop dramatically. In some documented cases, small Aircrete dome structures have been built for just a few $1,000s in materials, not hundreds of thousands, not even tens of thousands, a few thousand. Of course, that doesn't include everything: land, permits, utilities. Those can change the total. But the core structure itself, shockingly low. And this is where the contradiction becomes impossible to ignore. You have a building method that is cheaper, more energy efficient, fire-resistant, and simple in composition, and based on principles that are easy to understand. So why isn't this the standard? Why isn't this what new neighborhoods look like? Why aren't developers building entire communities this way? Why are most people still living in structures that are more expensive to build and more expensive to maintain? Take a moment and think about your own home. How much of what you pay every month is actually going toward keeping the environment inside stable? Heating systems, cooling systems, insulation upgrades, energy bills that fluctuate depending on the season. Now imagine a structure where most of that pressure is reduced, not by adding more technology, but by changing the way the house itself works. Wouldn't that make more sense? Or at the very least, wouldn't it be worth exploring? Because at this point, it starts to feel like we're not just dealing with a different building method. We're dealing with something that doesn't fit the system we're used to. And when something doesn't fit, it usually doesn't spread. But to understand why this kind of structure feels so out of place today, you have to go back to a time when it wasn't. Back to when curved structures and simple materials weren't considered alternative at all. They were the standard. And that's where this story really begins, long before modern construction methods existed, before insulation ratings, HVAC systems, and standardized building codes. People were already solving the same problem we're trying to solve today. How do you create a space that stays stable, no matter what's happening outside? And surprisingly, their answer looked very similar to what we just described. Not square, not framed, but curved. One of the most famous examples still stands today. The Pantheon in Rome, a massive dome built nearly 2,000 years ago. No steel reinforcement, no modern engineering software, no industrial materials. And yet, it's still there. Uncracked, uncollapsed, still holding its shape after centuries of weather, earthquakes, and time. Now think about that for a second. Modern homes are designed to last a few decades without major repairs. This structure has lasted nearly 2 millennia. So, what did they understand that we don't use anymore? The answer is surprisingly simple. Shape. A dome doesn't behave like a flat wall. In a typical house, weight pushes down vertically. That force creates stress points, especially at joints, corners, and connections. That's why modern construction needs reinforcement everywhere. Beams, studs, supports. It's constantly fighting against gravity. But a dome works differently. Instead of resisting force, it redirects it. Every bit of weight, whether it's from the roof, wind, or even snow, gets distributed along the curve. There are no concentrated weak points. No corners where stress builds up. The entire structure works together as one continuous system. This is called compression. The forces are always pushing inward and downward along the shape, keeping the structure stable instead of pulling it apart. And here's the key idea. A dome doesn't need a skeleton. The shape itself is the structure. Now, if you combine that geometry with the right material, you get something incredibly efficient. That's where Aircrete comes in. Remember those tiny air pockets we talked about? They don't just help with insulation. They also reduce weight. Traditional concrete is heavy. Very heavy. Which means the structure has to support a lot of mass. Aircrete, on the other hand, is much lighter. Sometimes up to 5 or 6 times lighter than standard concrete. That changes how the structure behaves. Less weight means less stress. Less stress means fewer structural demands. And because it's still a cement-based material, it doesn't burn. It doesn't rot. It doesn't attract pests. So now you have a structure that is lightweight, fire-resistant, insulating, and structurally efficient, all at the same time. Now compare that to a typical modern wall. You have a wooden frame. Inside that frame, insulation. Then drywall. Then exterior sheathing. Then siding. Multiple layers. Multiple materials. Multiple points of failure. Each layer has a purpose, but each connection between layers is also a weakness. Air leaks. Moisture intrusion. Thermal bridging. All of these reduce performance over time. But a dome made from a single material doesn't have those layers. No internal cavities. No hidden gaps. Just one continuous shell. And that changes how the building behaves in real life. Let's go back to temperature. In a traditional house, heat moves quickly. If it's cold outside, the warmth inside escapes through the walls. If it's hot outside, that heat pushes its way in. That's why heating and cooling systems are constantly running. They're compensating for loss. But in a thick, continuous wall like Aircrete, heat moves slowly, very slowly. So instead of constant temperature swings, you get stability. The interior doesn't react instantly to outside conditions. It lags behind. And that delay creates comfort. During the day, the structure absorbs heat gradually. At night, it releases it slowly. It smooths out the extremes. Now imagine living inside that kind of environment. No sudden temperature spikes. No constant cycling of systems turning on and off. Just a steady, controlled interior. And here's where it gets even more interesting. This isn't theoretical. There are real-world examples of small dome structures maintaining comfortable indoor temperatures, even when external conditions are extreme. Hot climates, high humidity, direct sunlight, and yet inside, noticeably cooler. Not because of advanced technology, but because of how the structure itself behaves. So at this point we have to stop and ask, if this shape has worked for thousands of years, and this material improves insulation, reduces weight, and increases durability, Why didn't construction move in this direction? Why did we end up with buildings that rely so heavily on mechanical systems instead of structural efficiency? Because based on everything we've seen so far, this isn't an unproven idea. It's not experimental. It's not new. It's built on principles that have already been validated over centuries, which makes what happens next even harder to ignore. Because the reason this kind of structure isn't everywhere has nothing to do with whether it works. It has everything to do with what happens when you try to build one today. So if the structure works, if the material works, and if the cost advantage is real, then something else must be stopping it. Because technologies that are cheaper, simpler, and more efficient don't usually disappear on their own. They get replaced, or they get pushed to the edges. And in this case, it's not an obvious rejection. It's something much quieter. It's friction. Let's start with the first layer of that friction. Building codes. Most residential construction today follows very specific guidelines. Approved materials. Approved methods. Approved dimensions. Wood framing. Steel. Concrete block. These are all clearly defined. There are tables, rules, step-by-step pathways. If you follow them, you can build. But Aircrete domes? They're not part of that system, which means they fall into a different category. Alternative construction. And that one word changes everything. Because, now, instead of following a clear path, you have to prove that what you're building is safe. Not in theory, but through documentation, engineering reports, structural calculations, material testing, all of it. And none of it is free. In fact, it can cost more than the structure itself. Think about that. You could build the physical dome for a few $1,000s, but spend tens of thousands just proving that it should be allowed to exist. The material is cheap. The permission is not. Now layer on the next issue. Inspection. When a building inspector shows up to a standard house, they know exactly what they're looking at. They've seen it hundreds of times. They have checklists, clear expectations. But when they see something unfamiliar, something outside the system, there's uncertainty. And uncertainty leads to hesitation or rejection, not because the structure is unsafe, but because it doesn't fit the template. Now add another layer. Appraisal. Let's say you successfully build your dome. You invest time, effort, and money. You create something durable, efficient, and unique. Then you try to assign it a value. That's where the problem starts. Appraisers rely on comparisons. They look at similar homes in the same area, same style, same structure, same materials. But what happens when there are no comparable homes? What happens when your structure doesn't resemble anything around it? It becomes difficult to value. And when something is difficult to value, it often gets undervalued. Or worse, treated as having no clear market value at all. Now think about what that means. If your home can't be properly appraised, banks won't finance it, which leads to the next barrier: loans. Most people don't build homes entirely out of pocket. They rely on mortgages. But lenders depend on predictable assets. They want properties they understand, properties they can resell, if necessary. A unique dome structure, built from an unfamiliar material? That's risk. And risk gets rejected. So even if the house is functional, even if it performs better than a conventional home, it becomes almost impossible to finance. Now add insurance. Insurance companies operate on data. They need historical information. Thanks for watching. Failure rates, fire behavior, damage patterns. For standard construction, that data exists. For alternative structures, not so much, which means insurers don't have a category. And if there's no category, there's often no policy. So now you have a house that is hard to approve, hard to inspect, hard to value, hard to finance, and hard to insure. Not because it fails, but because it doesn't fit. And this is where the pattern becomes clear. Nothing explicitly says, you can't build this. There's no single rule blocking it. Instead, every step becomes slightly more difficult, more expensive, more uncertain, until most people simply don't try. Now here's the deeper layer. Why is the system structured this way? Why is everything built around repetition? Instead of efficiency, the answer isn't technical. It's economic. Think about how modern housing works. A traditional home isn't just a structure. End quote. It's part of an entire ecosystem. Materials suppliers, contractors, energy companies, maintenance services, insurance providers. Each part depends on ongoing activity, ongoing cost, ongoing need. Now compare that to a structure that requires fewer materials, consumes less energy, needs less maintenance, and lasts longer without intervention. What happens to the ecosystem around it? It shrinks. There's less to sell, less to service, less to replace. And here's the uncomfortable question. What happens to an industry when people stop needing it as much? Because a house that doesn't require constant heating doesn't generate the same energy demand. A structure that doesn't degrade quickly doesn't create recurring repair cycles. A design that simplifies construction reduces complexity across the board, and systems built on complexity don't naturally evolve toward simplicity, not because anyone is actively stopping it, but because everything is already optimized for the current model. Training programs, supply chains, regulations, financing structures, all aligned in one direction. So when something comes along that doesn't fit, it doesn't integrate. It stalls, not through prohibition, but through resistance. And this pattern doesn't only apply to Aircrete domes. You see it in other areas too. Passive solar designs, earth-based construction, off-grid systems, technologies that reduce dependency, often struggle to scale, not because they fail, but because they don't create the same continuous demand. And that's the key distinction. This isn't about a material being disallowed because it's unsafe. It's about a system that doesn't have a place for it. Which brings us to the final question. If all of this friction exists, who is actually building these homes today? And how are they managing to do it, despite everything stacked against them? So if the system makes this kind of house difficult to build, who is actually doing it? Because despite everything we just covered, the permits, the financing issues, the lack of standard pathways, these homes still exist. And not just as isolated experiments. There's a small but growing group of people building them. Not large developers. Not major construction firms. Individuals. Owner-builders. Small communities. Independent designers. People willing to step outside the standard process. And what's interesting is how they approach it. They don't try to fight the system directly. They work around it. Some choose locations with fewer restrictions. Rural areas. Unincorporated land. Regions where building codes are minimal or loosely enforced. Others take a different path. They go through the full approval process. They hire engineers. They document everything. They spend more on paperwork than materials. And that's where one of the most revealing moments happens. The cost inversion. In several documented cases, the structure itself, the dome, the walls, the shell, costs less than the permits required to approve it. Think about that. The physical home, cheaper than the permission to build it. 3. Not the land, not the utilities, just the right to construct something different. And that flips the entire idea of affordability on its head. Because the limiting factor is no longer the material. It's the system around it. Now, if you zoom out, something else becomes clear. This isn't happening everywhere. In fact, in some parts of the world, materials like Aircrete are completely normal. In countries like Germany and the UK, similar lightweight concrete materials are used in a significant portion of residential construction. Factories produce them at scale. Builders are trained to use them. Codes include them. They're not alternative. They're standard. Same material. Same physics. Different outcome. Which raises a simple question. What changed? Not the science. Not the performance. Just the system that surrounds it. And even within more restrictive regions, you still find pockets where these ideas survive. Workshops teaching dome construction. Small-scale projects documented online. Communities experimenting with low-cost housing. People sharing methods. Refining techniques. Improving the process over time. Because once you remove the external barriers, The logic becomes hard to ignore. Lower material cost, lower energy demand, fewer components, long-term durability. It's not perfect, and it's important to be clear about that. Building one of these homes isn't as simple as mixing materials and pouring a dome. There's still labor involved. There's still skill required. And depending on where you build, there can still be significant legal and financial challenges. So this isn't a magic solution. It's a different approach, one that trades complexity for simplicity, but requires stepping outside the default path. And that's the real dividing line. Most systems reward conformity. They're designed to make repetition easy. Same materials, same methods, same outcomes. Because repetition creates predictability. And predictability makes everything from financing to insurance work smoothly. But the moment you step outside that pattern, everything changes. You're no longer following the system. You're navigating it. And that takes effort, which is why most people don't do it. Not because it's impossible, but because it's unfamiliar. Now, step back and look at the bigger picture. You have a structure that can be built at a fraction of the cost, reduces reliance on energy systems, simplifies the way a home functions, and challenges the assumptions of modern construction. And yet, it remains on the edge, not widely adopted, not commonly discussed, not fully integrated, because the system we live in doesn't just build houses. It builds expectations about what a home should look like, how it should be constructed, how it should be financed, and anything outside of that feels out of place. But here's the final thought. The dome doesn't care about those expectations. It doesn't know what a building code is. It doesn't know what an appraisal system is. It doesn't know what materials are considered standard. It follows a different set of rules. Physics. The same principles that held ancient structures in place for thousands of years. The same behavior of heat, air, and mass. Those rules haven't changed. What has changed is how we choose to build around them. So the next time you think about housing, about cost, energy, and long-term sustainability, it might be worth asking a different question. Not just what is available, but what actually makes sense? Because sometimes the most efficient solutions aren't the ones that failed. They're the ones that never fit the system in the first place. And if you want to keep uncovering ideas like this, the ones that quietly exist just outside the mainstream, make sure to subscribe. Because once you start seeing the pattern, it becomes a lot harder to ignore.